group from this section. I did not get the other groups. So you have until tomorrow maximum to form your groups. Otherwise, what I will do, of course, that the group that was formed, that's B1 group, but I will go through the remaining students and I will just divide you by the number in this section. So the first 8, then the second 8, the third 8, and so on. I don't like to do that because you will start knowing each other and you'll start. I always like to give you the chance to form your own teams. But I have received only one team from this section. Okay, so you have until tomorrow maximum. And if I don't receive them by tomorrow noon, maybe I will have to send you the team names by the end of today, because Wednesday we will start working on the project. Okay. You have any questions? Other questions? Okay. The answer for the homework will be released today, inshallah, after the deadline passes. To give everyone a chance to submit your work, and you can have a look at it because yes, it is included in the quiz. Okay, so today, inshallah, we are gonna start our design part of the course. We have spent quite some time in the basics part, chapter 2 and 3, aerodynamics and propulsion. Then we developed the equations of motion, chapter 4, and chapter 5 we looked at some performance characteristics on steady flight. We were talking about climb, glide, cruise, landing, cruise, range, endurance. Then we talked in chapter 6 about accelerated flight, turns, takeoff and landing. So in chapter 7, what we will do is that we are going to develop the philosophy of the airplane design. And this philosophy is not something that someone would sat down and just decided, let's design the aircraft this way. No, it was a developing process over more than 100 years since the aviation industry started. And we are going to see how you can see my screen, right?
Yes, we can.
Okay. So we will see how this design process evolved into 3 main phases: the conceptual design phase, the preliminary design phase, and the detailed design phase, which are followed by virtually all design projects from a home-built aircraft to the Airbus 380. And then we are going to introduce the different parts here in the textbook called pivot points, intellectual pivot points, that make the conceptual design phase. And why the conceptual design phase? Because it is the design phase that's taught in universities. Every single airplane vehicle design course, just like this one or the EE 427, deal with the airplane conceptual design phase. Okay. Yes, Faris.
Doctor, I don't know if it is a problem from me, but I can see the screen.
Yes,
Can anyone confirm there is a problem with the screen?
yes, also me.
Yes, for me also.
Oh, but I asked and you told me you saw it. Okay.
Yeah, at the beginning we were able to see it, but then it disappeared.
Okay, let me do this again. What about now?
Yes, now we can see it.
Okay.
Yes.
Okay. So what we will do today and what's covered in chapter 7, which is a relatively short chapter without a single equation. is that we are going to look at the phases of the airplane design: conceptual, preliminary, and detail. As I told you, conceptual design is the one taught in universities, where we start with the requirements provided by some client. That client in real life would be the aviation industry, the airlines, some market survey someone would do to find out gaps in the market that need to be filled. And then conceptual design phase, go through developing the aircraft from the requirements. Remember, in the requirements, we don't have an aircraft. It's not like the problem solving that you are doing in homework, where someone will give you all the information about the aircraft, tell you check the range, find CLmax or whatever. Now that's different. What's given in a real design problem is the requirement. We want an aircraft that has a certain range, certain rate of climb, a maximum takeoff distance of no more than this, and it carry that many people, and we want it as economic as possible. Go ahead and find that design. So these are the set of requirements. That's the first pivot point in conceptual design. And these requirements are then used with the information that we have learned so far in order to estimate the weight of the airplane. Okay. For example, one way to do this, of course, we are going to do this in details throughout the next 3.5 to 4 weeks. One way to do this is to use the range equation, which I'm sure now you are familiar with because it's in the homework, where you find the range as a function of what are the parameters that are there in the range equation are equal. What parameters do we have in there?
For jet or propeller?
Whatever. Let's say propeller.
Specific fuel consumption.
Specific fuel consumption is there.
CL over CD.
CL over CD, the aerodynamic efficiency is there.
And the weight of the airplane with full fuel and without fuel.
Yes, the weight at the beginning of the mission, full fuel, end of the mission, almost no fuel. Okay, maybe the speed in one of them, you might find the speed as well of the aircraft. So what we will do is that we're going to take the same equation, but rather than finding the range as you do in the homework, we are going to have the range as the requirement. We will know the range, 2,000 miles, for example. And the unknown in the equation will be the weight of the aircraft. So this is one way to estimate the weight of the aircraft, to use the performance equations that we had, but making the unknowns are the parameters of the aircraft, not the requirements. Okay, so the next step would be estimating the weight, and we're going to do this again in chapter 8. We will do all these steps in detail in chapter 8 on one example, and you will do it on your design project. And after we estimate the weight, and in the process of estimating the weight, we will have some shape of the aircraft. We will develop how would the fuselage look like, what's the wing airfoil, would it be tapered or not, swept or not. You will make decisions in this based on the study that we had. So for example, we will decide on whether to sweep the wing or not based on the fact that we know sweep is usually for fast aircraft. And if you want to stabilize the aircraft, this is how we build sweep. So you will decide on whether it's going to be swept or not. Afterwards, we are going to calculate some critical performance parameters. That means we will agree on, for example, what's the wing area? That's a critical design parameter. What's the wing loading? What's the thrust to weight ratio? All these numbers that appeared in the equations, we will find them here from the initial sketch or concept that we develop. And then we will finalize the layout using these performance parameters. That means we'll start putting dimensions on the drawing, and we will have a better estimate of the weights. Then we will do some performance analysis. That means we'll check if we satisfy the requirements, and we will optimize the design trying to improve the performance to the best that we can. So these are the parts of what's called the intellectual pivot points. We are going to cover them in more detail in a few minutes. Okay. But before we get there, let's talk a little bit about the difference. Let me hear if you have like any idea of a difference between conceptual, preliminary, detailed design. And I didn't ask this question in section 2 because I know most of you here have taken AE 220. So let's see. What's your perception of when I say conceptual design? What do you expect that you will do? If I tell your team will do conceptual design, what do you think you will do?
Maybe choose CL over CD ratio and wing load ratio.
Okay. What else? Because for many, when we say conceptual design, it's just like drawing the shape, like it's more of an art.
Conceptual design يعني على موضوع معين on one concept.
Yes. What do you mean by the concept here?
مثلا يعني تبى تركز على الوينج لودنج، على specific fuel consumption، تبى تركز على شيء معين concept واحد وتسوي design عليه.
Okay, if that's what you're saying. Okay. So we really need to be on the same ground in this. That's why I asked what do you have in your mind before I tell you what does the word conceptual design mean here. So what else? Anyone has, when you say conceptual design, because for me, for example, when I say conceptual design, I thought it was like take a piece of paper, a pencil, and draw the concept of the aircraft. This is how it's look like. If you look at a magazine, they tell you conceptual design or artistic design. It's more of a shape, right? That doesn't involve calculations or anything. But in real life, it's none of what we have said, none of what you have mentioned, and it's not the one that I have just said. Okay. By conceptual design, and we're gonna see it here, we are gonna have as much as basic information of the aircraft as possible. So at the end of the conceptual design phase, that means for you at the end of week 15, for a real company at the end of 6-month period, because it's developed in about 6 months. No, who's presenting? Who's presenting? Nawaf, are you presenting something?
معليش بالغلط يا دكتور.
Okay.
أحط كانسل بس عشان ما.
No, that's okay. So at the end of the conceptual design phase, we will have almost the shape fixed of the aircraft, dimensions fixed, performance checked. So it's not a drawing and it's not one topic. It's all of these. It's all the aircraft, as we're going to see now in a few seconds. Okay. So it has an artistic part and it has a science part and it has an experience part. And it's valid for any type of design. It's not only airplane design. What you have learned is valid for wind turbine design. When we talk about flow, about propellers, train design because of aerodynamics involved in there, boat designs because they are vehicle moving in a fluid. So the steps that we had, have seen will go like this. In conceptual design, we don't focus on one part. We develop the concept of the aircraft. What does that mean? It means for a team that we will sit and we will decide, not just select, decide, is it going to have 2 engines or 4 or 3? Is it going to have a high wing? Is it above the fuselage or a low wing? Will it be swept or not? Conventional tail or the horizontal tail will be on the top of the vertical stabilizer. Are the engines going to be attached to the fuselage or they are going to be under the wing or maybe above the wing? Okay, so developing the concept here means answering the question how it's going to look like, and each decision of these will have consequences. Each decision might mean an increase or decrease in performance, an improvement in maintenance, or a decrease in the operation capabilities of the aircraft. So as we go, we have to understand the effect of these decisions so that we can make the right ones. Then we have also to, when we do these decisions, to make sure that we understand what's the driving requirement. For example, if we're talking about the design of a transport aircraft, the driving requirement is economy, the fuel consumption, the cost of operation. So it is economy at the end of the day. So although you have many performance characteristics like the rate of climb, the take landing distance, and you have to satisfy all of them, the one that will probably be critical, and by critical means most difficult to satisfy, will be the range requirement and the weights so that we can have an economical aircraft. If you are talking about an interceptor aircraft that has to climb real fast to intercept enemy aircraft, maybe the driving requirement would be the rate of climb, not the takeoff distance, not the economy, not the payloads. If so, every design will have a certain driving requirement that will probably be the most difficult. It's the one that will demand certain decisions. As I told your colleagues, it's like when you plan your courses for next term 202. When you start selecting you will probably have one course in your mind that's going to be the most difficult, or the most demanding, or they require a lot of work, or you have heard your colleagues is not a good grade is not guaranteed in that course, whatever. That course, that requirement will dictate the selection of other courses, for example. So you need to have an easier course that goes with it, or you don't need to have 2 labs together. So one driving requirement will probably push and have an effect on all your decisions in the design. Also in the conceptual design phase, you will have to do some trade-offs. For example, if there was a requirement on the range to be not, let's say 2000 miles, you can satisfy that with a certain weight. But as a designer, you should report in your design that if the range is decreased to 1800 miles, maybe the weight reduction will be so and so. So that you allow the client the opportunity to make choices. So you do some trade-offs, give and take. If you allow a shorter range, I will give you a lighter aircraft by that percentage and a cheaper aircraft. Would you be interested in that? So all these trade-offs are part of conceptual design. And finally, overall, how would this design cost and weigh? What would be the cost of this design? Because money is an important issue. Otherwise, no one's going to buy the aircraft if it's not economical. Okay. So why are all these important? Because conceptual design phase is in many cases the determining factor in whether the whole project will go on and continue, like the X-35 became the F-35, or it will be rejected, just like the Boeing version that applied to the same competition when the US was developing the newest fighter. So Lockheed Martin provided the X-35, Boeing provided a similar one, and back then Douglas had like a variation of the F-15 Eagle. And here, this one was rejected after the conceptual design phase. They were not allowed to proceed beyond that. So each company would, back then they were separate companies, but now they have merged. Each one would provide a conceptual design. That means something like the theme of scale, something like what you would do in AE427, for example, a report, a demonstration that the design can satisfy the requirement. So one was rejected after the conceptual design phase, so it will not proceed. So the company lost the money invested in the engineers and developing the conceptual design. Then money was allocated to Boeing and Lockheed Martin to proceed after the conceptual design phase. So they went to preliminary design, detailed design, and produced one prototype. Then the Boeing was rejected after the demonstration of the prototype, and that one was selected. So my point is, conceptual design is very important because it can mean an early terminal of the project. Okay. Any questions in conceptual design so far? Now, conceptual design I mentioned is the one taught in universities. So your report will be a conceptual design phase. In AE 427, after about 4 months of work, it will be a conceptual design phase, because it's not merely on one item or an overall view. It will have some details in there. So the outputs of the conceptual design would be the shape, the size, the weight, and the performance characteristics of the aircraft, a layout of the aircraft, drawn maybe on CAD system, SolidWorks, whatever. Okay, sometimes with numerical CFD results, not only hand calculations. And in developing this design, you will use all the topics that you have learned so far: aerodynamics, structures, propulsion, performance. That's why people sometimes call the design the fifth discipline of aerospace engineering. After the common four, it would be the fifth because it involves all of this. Okay. Any questions in the conceptual design? All the 7 pivot points are involved in this conceptual design. So takeoff distance, the landing, the turning, wing loading, CL max, flaps, no flaps, even cost, all of these are involved in this conceptual design. And you will do this as a team. Okay. Afterwards, we have the preliminary design phase. It takes about 1.5 to 2 years for real aircraft after the 6 months of conceptual design, typically. Times became shorter now, but it would take about that time. Here, no major changes are allowed in the design. That means if it was decided that the wing sweep is going to be 35 degrees, it will remain 35 degrees. Okay, but here small minor changes might arise from optimization of the design. Here, where maybe a prototype can be produced, wind tunnel tests, designing of the hydraulic system, pneumatic systems, landing gears. Here, where the market survey data would play a role. For example, in the conceptual design, we had an estimate, or we develop an estimate of the aircraft based on historical data. But as time passes, marketing personnel in the company will attend, for example, Dubai Air Show, Farnborough Air Show. They will contact airlines and they are going to start talking, hey, we have this sort of a design of this aircraft that has this capability. Will your company or airline be interested in it? So they might have some letter of intent from airlines to purchase maybe 50 aircraft, from another aircraft 30, and so on. They might have confirmed reservations from clients, and the company would use these numbers in order to improve the cost estimates. Because, for example, the initial estimates was based on producing 500 aircraft. Now, after they made the marketing, they found out that only 300 aircraft might be sold. So that means they have to refine the cost and push it a little up, because the aircraft is going to be more expected than initially thought in the conceptual design. Okay, so things take time and they go hand in hand, engineering with marketing and so on. Maybe changes occur in the oil industry that will drive the oil cost either up or down. Maybe changes will occur in the manufacturing that will drive the manufacturing cost down. So all of this will affect the cost estimate in the preliminary design. Then the preliminary design will be followed by the detailed design, where technically here you design all the nuts and bolts and panels, frames, ribs, seats, entertainment, electric wiring, every single thing that's going to be manufactured. Also, you will be, not you, engineers will be designing, because here we will involve so many engineers from different disciplines. You will have mechanical engineers, manufacturing engineers, electrical, computer, chemical. You are going to have people from Department of Chemistry, graduates of Department of Chemistry, for all the departments, sometimes even civil engineers. And they will be designing, for example, the machines that are going to be used in producing the aircraft, the jigs, the dies, operating the tools, all of these are going to be here in the detailed design. Producing the drawings that will go to the workshop for manufacturing. Determining how many rivets to attach each part to another part. What's the diameter of the rivets? What's the diameter of the hole of the rivets? How we're gonna make that hole, drill that hole in the skin. And writing down the process for the worker in the workshop to do that hole. And then how to put that rivet, how to finish it, how to trim it, and people of quality control, how to check the strength of that rivet, and so on. So all of this here in the detailed design phase. As I mentioned, all the steps that we have seen in the introduction, all the steps that we do here, all the steps that are being done in any design course, aerospace design course in university, is in the conceptual design phase. The part of manufacturing and producing is typically done for a smaller scale. So for a prototype, for a project, but for the whole aircraft, it's done on a company because it needs the experience to make decisions. It needs the resources, and in many cases it has to be like a government work. In many cases, not just private work. Okay. On smaller scale, it could be a privately owned company, for example. The 7 points that we have talked about, and we are going to go through them now in detail, because this is basically what you will be doing starting next Wednesday, are called these intellectual pivot points in the textbook. So I will stop before I proceed to see if any of you have any questions in the conceptual, preliminary, and design and detailed design phases. Okay, so here how it goes. A client would start to have some requirements. In your case, I will be the client. In real life, it would be the aviation industry. It could be a country. It could be the Air Force of a certain country or a branch, whatever. It's just like any other requested item. It starts with the requirement. They publish a set of requirements in what is called the request for proposal. Very similar to what you see on newspapers like مناقصة, زي المناقصة كده. Okay, but it's a set of requirements. We are looking for an aircraft with these capabilities. Then design teams in different companies, in your case, in different teams in this section, would start to sit together, think, develop a concept, and see how they are going to satisfy this requirement. Okay. And at the end of the conceptual design phase, they provide the proposal of them. So that's why I will publish request for proposal on Wednesday, and you will submit me on week 15 that proposal. In the proposal, they take the requirements, start to develop a concept. And of course, you are not going to do this from scratch on your own, because this is the topic of chapter 8. So here in the lecture, I will be going through chapter 8, how to go through one step from here to the other in designing a propeller aircraft. And you will be doing the same in your design project with a different set of requirements with a different aircraft. So from the sketch, we will be able to develop an estimate of the total weight. In the process, we will estimate L over D, for example, of the aircraft. Remember, we don't have the information here. No one is going to give you the values until you find the maximum value of L over D. No. You will need it in order to determine the weight, so you will figure out some way to do it. In problems and homeworks and quizzes, you had a chart of an airfoil to look for. Here, we don't know even what is the airfoil. So you have to choose the airfoil based on the requirements. Which one will have a good chance of satisfying the requirements? And after you develop the concept, then you will start finding the critical performance parameters. In the concept, we agree that it will be, for example, swept wing, tapered, with a certain taper ratio. Maybe the aspect ratio is so and so. But we don't have the parameter. I don't know how big the wing is going to be. We don't know what's the wing area. In this part, chapter 3, we will develop this information. So we will estimate CL max, and there was a question by Faris early this morning, how do we get CL max? Well, as a student in a class solving a problem, CL max is in the book, in a table or a chart. But as an engineer outside the university, he has all the resources on the board to get a reasonable value of CL max. Okay, so he can make a model and put it in the wind tunnel, take measurements if he has a different airfoil. He can pick a particular type of airfoil where he has that value of CL max. We can resort to historical data of several aircraft. I can make a solid works model, mesh it, put it on ANSYS Fluent or Xfoil or whatever, and get the CL alpha variation and find CL max. Yes, Hassan.
How can we get CL max if we don't know the type of the airfoil?
Yes, from, you see in 1, 2, 3 here, there is a missing part. It's called developing the concept. And in developing the concept, you will agree that with the team, of course, you will decide we will have a swept wing, we are going to have that taper. This is a fast aircraft, so it should be a thin airfoil. Other aircraft we're using the 5-digit series, okay, but I want a certain L over D ratio. So, or a high L over D ratio, for example, or a high stall angle, whatever the requirement. So I have these 2 or 3 airfoils to choose from. Let's look at them, which one gives better results, and now I will choose that one. So you will choose the airfoil. It's not given, you will choose it. Okay. Now that you have chosen it, then you have to find out what's CL max of that particular wing. Shall I use the one for that airfoil, or maybe it will go down a little bit because of the 3D effect? Okay, so all of this we're going to have. We're going to touch on these areas, this term here, and you are going to have them in more details, inshallah, in AE 427. Okay, Faris, yes.
Will there be one clear choice that we should get, or will there be multiple choices?
I didn't get the question. Can you repeat the question?
So is there one clear choice, for example, for the wing that is optimized, or that you have in your mind, or will there be multiple choices that there is no right choice? I mean, there is no one.
Very good question. Very good question, and brings me to the point. When inshallah you graduate and you want to own your own car or replace your old car or want to buy someone or some car, is there the best car in the market that you will go and buy, or do you have choices?
Choices.
Because there isn't the best design. The best design has not been done yet. There are many answers. in a design course, there is not the right answer. Okay, there is a good answer and there is a better answer, but there isn't the best answer. There is a range. For example, even if you look at 5.3, the table that Faris was asking about how to get CLmax, there's not a value. There is a range. There are variations in the design. So of course, once you get to the point of design, there is not like the right answer. There is not a model answer to the question. Okay, there are choices that make sense. The choices that are justifiable. So for example, I can choose to have under the wing to improve the maintenance of the aircraft. That will make maintenance easily because we can maintain the engines while we are walking around the aircraft. But if the engines are on the fuselage a little bit higher, I will need a ladder. That will make maintenance more difficult, and that's an issue. Okay. Now that doesn't mean all aircraft will fly now with engines attached to the under the wing, because there are other issues. If this aircraft is going to be operated from not a very clean runway in the desert, for example, where it might land on compact sand, the engine, the intake is going to digest a lot of sand, and that will shorten the time of the turbine blades. So there isn't really a clear choice. There is the good choice for this design, and there is the bad choice for this design. Okay, and this is the part where these choices are being investigated here at the beginning, right before that. You will do this within a couple of weeks. But once we have these choices, once we agree on the different choices, we are going to start finding the performance parameters according to these choices. If I choose the airfoil, the sweep, the taper, the location of the wing, I will be able to estimate what would be CLmax in this case. L over T, what's the value? I will calculate the wing loading, maybe from the requirement of the takeoff distance. If the takeoff distance should not be more than 2,000 feet, I can determine the wing loading in this case. I will calculate the thrust to weight ratio. And guess what? From these performance parameters, together with the weights, I will be able to configure the aircraft. Because what will happen if I take the total weight of the aircraft with the wing loading? What will you get? If I use this piece of information, the weight and the wing loading, what will you get? What can you get out of these two pieces? The wing area. So you will know the wing area. Remember, we have selected the sweep, the taper, but I really don't know how big the wing is. So dividing these two values, the weight over W over S, I will get the wing area. If I have the wing area, taper ratio, aspect ratio, now I will have dimensions. I can start drawing the wing because I will have dimensions now. If I have the weight and divided by the thrust to weight ratio, and where I'm going to get the thrust to weight ratio, maybe from the climb equation. If I have a condition of the climb, T over W will be my unknown in there, not the rate of climb. So I will get T over W and I will get the weight. If I divide T over W by the weight, if I multiply D over W times the weight, I will get the thrust of the engines, 10,000 pounds. Then I might decide on achieving the thrust by 2 engines, each producing 5,000 pounds, or 3 engines producing 3,300 pounds. So now I know what would be the dimensions of the engine, how big it is, because I know the dimension of the engine of a thrust of 5,000 or 3,000. I can find it in the market. So now I can start putting the configuration of the aircraft. I will start putting the shape and the size of this aircraft, engines, wings, and if I size the wing, then I will be able to size the tail from stability. And then I will start sizing the flaps and the control surface. Then I will start sizing the fuselage, how wide the fuselage is going to be depending on how many seats I want to put side by side. The length of the fuselage from aerodynamics and how many seats, rows of seats, and so on. Okay. So now I can draw the aircraft on SolidWorks, on AutoCAD or whatever. I have dimensions. But at this time, after pivot point number 4, we will stop and say, hey, we estimated the weight back then based on just a sketch of the aircraft and some range equation that we had. But right now, after step number 4, I have a drawing with dimensions. If I use this information, will it change my weights? Yes, it will give me a way better estimate of the weight. It could be higher, it could be lower. We don't care, but it will be a better estimate of the weight. Because now we have more information into the weight equation. Okay, so we will estimate the weight. And with the new weight, we will check again the performance parameters that we have. Okay, so we'll see if they are exceed the performance requirements, or it will be less than the performance requirements, or it will not change at all. And if I need to change something, I will go back, change L over T, change the wing loading, change LS, do some major design decisions. Once this is done in the whole cycle, and the design is confirmed, the configuration is finalized, we can start optimizing it. Like putting icing on the cake. So would we have a winglet to the wing? Would that improve L over D a little bit? Would that give us a better satisfaction of the requirement? If we change the shape of the intake, would that reduce the fuel consumption a little bit, and so on? Okay. Any questions? Okay. So in doing these 7 points, we will use the information that we have learned, but you don't have to use them the way you solve a homework or a quiz using a pencil, a piece of paper, and a calculator. Because as you see here, we have an iteration process that might go on. So it would be wise to program the process maybe on Excel or MATLAB or whatever programming language you are familiar with, because you will do calculations several times. So if you keep doing them by hand, you'll just be wasting time. But if 2 of the team members, for example, program the process of the performance parameter calculation, they will help everyone do the cycle several times without wasting time. So you will need to learn, to use any programming language that you are familiar with. You need to use some tools that might help get CLMax, CD, not K. And as mentioned earlier today, there isn't the best way or the only way. So one team might use Xfoil, for example, to produce CLMax. Another team might use airfoil data. A third team might use a Profoil. Some of these you will learn in your aerodynamics courses, which you haven't taken yet, I understand. But some are so simple that with a simple tutorial, you can use them within less than a couple of hours of watching a couple of tutorials. You can have your wing with the pressure distribution on its CLMax and so on. But by the time you get to the 4 to 7 course, you will probably have passed through all of these in different courses. I know ANSYS, for example, we have that in 3 to 8. Fluent probably in 333. So in different Xfoil and Profoil are so simple that we count on you to learn that. These are, so any of these would be okay. Any of these skills would be fine. I'm not restricting you to any one of them, and you are not restricted to the one in the textbook. Now, once you start, your team starts next Wednesday, in a couple of days, all individuals' work will count. So you can have individual tasks assigned to each student, and they all add towards the big project. I will give you the details of how things are gonna go on Wednesday, together with what exactly are the requirements, what the design project. But for now, it's enough to know that you will start on Wednesday, just like I will start chapter 8, and we will go hand in hand. by the end of week 13, your team will provide a progress report, short one, very short progress report that summarizes the work that has been achieved, what values were found, where are we on the 7 pivot points. And by the end of week 15, you will submit the final report, which will have all the 7 points in there, full design of the aircraft, including drawings, calculations, and all of this is called conceptual design. Then each team is going to present a very short presentation, 10 minutes per team only, 10 minutes per team. And because of the number of teams here, I'm having 2 sessions for this, Wednesday of week 15 and Sunday of week 16, which will be a normal Wednesday class to account for the National Day holiday. So on 2 sessions, all teams will be presenting in 10 minutes only. They will summarize their work. You can use PowerPoint or Visio, whatever software you want to present on. Okay, and there will be questions for individuals on their specific tasks on the project. Any questions?
Yes, Doctor. Can you repeat
Yes.
what you just said, please?
About?
Next week there will be a presentation.
No. Why
Okay.
would be presentation? You haven't designed anything. On Wednesday, I will provide the design project. I will tell you,
Okay.
here is what I want you to do.
Okay.
I want you to design a propeller aircraft that carries that many passengers through this range. These are my important requirements. I am the client.
Okay.
Okay, and you will start working and you will give a progress report after 3 weeks and a final report after 5 weeks. For those who were not with us early this morning, I received only the list of only 1 team. I'm giving you up to tomorrow, let's say tomorrow noon, to form other teams and send me. Otherwise, I will divide all of you into 4 other teams. Okay, the number of teams here in this class can be 5 to 6. I would say 5 would be reasonable. Okay, so we're going to have 7 or 8 members per team. Okay. If not, then I will go by the section number and I will just divide 8, 8, 8, and you will have to work together. But this is the last chance to form your own team. Send me team. I need 1 email from 1 member of the team with the 8 members or 7 or 6, sending them to me before noon tomorrow. I have to finalize them tomorrow so that we can work on Wednesday, inshallah. Okay, Shabab? Any questions? Okay, so